Okay, so good evening, everyone. Welcome to the third interaction session on design of steel structure. So my name is Devashish Panda. So you know, uh, let's quickly start this session. Okay, so during last interaction session, we have started the welding joints, or we have started discussing about the welded connections, and we went through the design specification and design processes of fillet weld. Now today, first we will, you know, cover the design of another kind of weld, that is butt, and then we will go through the plug and slot weld. Then we will spend some time on eccentric connection, eccentric bolted connection, and eccentric welded connection. Okay. So, before starting, please confirm that I am audible and the screen is visible. Yeah, please, someone. Okay, okay. So, butt weld. Now, this is one kind of weld. So, in fillet weld, what we have seen, that if we need to lap two plates, or we need to make a connection with some angle, then what we do? We go for the fillet weld. Now, when we need to join two members or two plates in a plane, back to back or face to face, then what will we do? We go for the butt weld. So how this butt welding is done? So look, here is the cross sectional view of the butt weld, and this is the plan view, top view. So if we see that there are two plates, okay, so basically what we do, we prepare these edges, and then we deposit that weld within that material. And during that process, yes, we need some backup plates and all these things. I will go into it. But yeah, we have an idea that butt weld, when we need to connect two members face to face or back to back, then we'll go for the butt weld. Now, this butt weld have certain advantages over your fillet weld. Like, think about it. This is Fe410 plate, and also this is Fe410 plate. Now, if we make this deposit material Fe410 or more than Fe410, so what this happen? This become a solid plate, right? So through this kind of joints, we can achieve better efficiency. Okay. Secondly, look at this. These are the most direct joints. Direct joints. So there is a chance of least eccentricity. And least eccentricity means, due to that eccentricity, whatever the forces and moments will induce, extra forces and moments will induce, we don't need to take care of this. Thirdly, they are very good at handling the cyclic loading rather than your fillet weld. So these are some sort of advantages, but we have some disadvantages also. Like what I said, through this butt weld, we can achieve better efficiency. Like, if I said, in mathematical term, so we can have, 99 or 100% efficiency. If we make this strength of this joint 100%, then obviously strength of the joint divided by strength of the solid plate multiplied by 100 will be our efficiency. So what we found out, that butt weld will resist or can resist more strength than your fillet weld. But most of the cases, the fillet weld is recommended. Now, why this fillet weld is recommended? Because of the most critical parameter is the handling with this kind of welds. Like, if we need to connect these two plates, what we need to do? We hold this plate using that crane, and we need to hold this plate using crane. Then we have to give a proper clearance. Then we need to make the joint. So that will create trouble when we will install this kind of things, because of less tolerance. Now think about it, when we need to lap two plates, so there will be much tolerances with respect to the side you know uh, modulations. So here we can see that the butt weld are more complicated to install in the site. So that's why most of the cases the fillet weld is used. Now let's quickly go through some properties of this butt weld. So we have two forms of butt weld. Two forms of butt weld. One is complete penetrated butt weld and another is incomplete penetrated butt weld. Now in complete or incomplete penetrated butt weld, what is the main difference here is the difference of throat thickness. Throat thickness. For incomplete penetration, we will provide different throat thickness. For complete penetrated butt weld, we will provide different thickness. Throat thickness. Now tell me, if the throat thickness TE or TT will change, what will change? The TT is directly proportional to your area of the weld, right? Now this area of the weld is directly proportional to your strength or load carrying capacity of the weld, right? Say PDW or FDW. That means if we increase or decrease the size of the throat thickness, what will happen? The load carrying capacity of the joint will increase or decrease. So later on we will know for the incomplete penetrated butt weld what should be the throat thickness, and for the complete penetrated butt weld what should be the throat thickness. So basically these two forms have the basic difference of the throat thickness. So here incomplete penetrated butt weld, the example of like single V, single U, single bevel, like that. And completely penetrated butt weld, we provide complete throat thickness on the two sides. So here double V, double U, and double bevel joints. Okay, so these are the basic forms of the welded joint. Now the thing is, what should be the throat thickness for completely penetrated weld, or what should be the throat thickness for incompletely penetrated weld? So our code IS 800 says that in case of complete penetration or in case of completely penetrated butt weld, the effective throat thickness is taken as the thickness of the thinner part. Thickness of the thinner part. Say for example, here we have a complete penetrated weld. Now say for example, this plate is 10 mm and this plate is say 15 mm. So what should be the effective throat thickness for this kind of joint? TE will be the thickness of the thinner part. That means 10 mm. Yes. Now in case of incomplete penetrated butt weld, what code says that code says the common portion you should take, but it is difficult to find out what is the common portion between them which get welded. So for this purpose, code says that you take 7/8 of the thickness of the thinner plate, and when you will calculate the stresses, you should take 5/8 of the thickness of the thinner plate for the incompletely penetrated part weld. Okay. Now we have the understanding of the incomplete and completely penetrated butt weld and what should be the throat thickness of this type of butt weld. Now the basic question comes in our mind, that what should be the load carrying capacity or what should be the strength of this type of weld. So let's go quickly into the strength part. So before going to the strength part, we need to know like effective length. So effective length, from the last introduction session we have known that the length up to which the throat thickness is maintained, up to which the effective throat thickness, more precisely the effective throat thickness is maintained, is called the effective length. Now code says the effective length of the butt weld should not be less than 4 times the size of the weld. That means L effective should be greater than 4S. We have to maintain this criteria. Now reinforcement. Reinforcement means it is the extra deposit. Like this is the surface of the plate, but here we provide some extra deposit on the both sides. And this extra deposit are generally provided 10%. So this extra deposit, why we provide this extra deposit? To increase the efficiency of the joint. And also, so think about it. This joint will expose to the weather. So there will be, uh, decomposition of this weld or wash out of this weld deposition. So to maintain that throat thickness throughout its life period, we provide some extra deposits. So it's the value of 10% generally provided on the other side. Now, what I'm talking about, what should be the strength of this type of welds? So what should be the strength? So before going to the strength, we have to understand what should be the mode of failure of this kind of welded joint. So think, what should be the mode of failure of this joint? So for example, I am applying a tensile force here, P, P. And if you see from the top view, now I am applying the load here, NP, pulling apart. My intention is to fail this joint. Okay. So tell me, in which stress or in which circumstances we consider this joint as a failure? Tell me. It's a solid plate. So what I said about the solid plates, there is no hole is made. That means we didn't reduce any kind of cross-sectional areas. So what will be the failure mode of failure criteria? It's the yielding, right? So if this kind of joints are subjected to direct tension, compression, then the failure will be governed by yielding. So what will be the design strength? The design strength will be the effective area. What is the effective area? Effective length into effective throat thickness into the yield strength, because this kind of joint will fail in yielding, or yielding will be the mode of failure for this kind of joint. And gamma mw, this is the partial factor of safety. The value of gamma mw we will find from the table 5. So 1.25 generally we take for shop welding and 1.5 for the site welding. So now we came to know that the butt weld, the design capacity of butt weld is governed by the yielding. Why? Because the yielding we consider as a failure, or most of the cases yielding phenomena will occur than the rupture, right? And if we consider the rupture one, then we have to consider that FU, ultimate, because to tear out something we need to reach out that level of ultimate tensile strength. Okay, now what about for shear? Shear also governed by the yielding. So for shear, this is the effective length, this is your strength, and some factor of safety. So here we come to know. Now remember one thing, that while designing that fillet weld, the design strength of the fillet weld was governed by the FU, not FY. So here we have the basic difference. Like butt weld, the design strength of the butt weld is governed by the yielding, but the design strength of the fillet weld is governed by the ultimate tensile strength, or minimum of ultimate tensile strength of parent material and deposit material, whatever it is. So what about the stresses? Like for butt weld, we consider generally the full stress equals to the stress of the parent material. But for the site specification, if we consider that this joint will made in the site, then these values are reduced to 80%. We are considered that no, the full strength of the plate will not considered, but we will consider below some values to be on the safer side, nothing else. So now we have the understanding that how to calculate the strength of this type of joint. Now if we know the calculation of strength, we can design this kind of joint. Like if the load is provided, we need to calculate the effective length, effective throat thickness, and all these things. And if effective length and effective throat thickness is provided, we can easily calculate the strength of this kind of joints. So let's quickly go through some example. So throat thickness, from where you can go to the throat thickness. So on the last class we have discussed this thing. So from table 22 we will get the value of K. So effective throat thickness T is equals to K into S, and this K value depends upon the angle between the fusion faces. So here if the fusion angle between the fusion faces is 60 to 90 degree, then we have 0.7, and consecutively we have the coefficient value with respect to the fusion angle. Now let's quickly solve this example. This is very simple example. What this example says, we have two joints. We design a suitable longitudinal fillet weld between two plates. We have two plates, one is 12 mm and one is 10 mm. Okay, now these joints need to transfer a factor tensile force to 50 kilonewton. And what is provided? The effective length of the weld is provided. Now check which joint is safe. So what we need to do? We need to find out the strength of the incomplete penetrated butt weld and strength for the complete penetrated butt weld. Now if this strength, the design strength of the weld is more than this 250 kilonewton load, then the joint will safe. If the design strength of this weld, a particular, say for example, incomplete penetrated butt weld, or complete penetrated butt weld is less than the applied load, then the joint will fail. So first, whatever your problem or what is the problem statement is given, first thing you will do, write a given data section. What data are given? So what data are given? So first we will take up this for single cover butt joint. So for single cover, not single cover, sorry, incomplete penetrated butt weld, or we can say it single V groove weld or butt weld. So for this section, what parameters are given? The factor load is given. The effective length of the weld is given 150 mm and the yield strength is given. Now tell me, this is the incomplete penetrated butt weld. Now we are calculating the stresses. So what should be the effective throat thickness? 5/8 of the minimum thickness of the plate. So 5/8 of the, which is the minimum thickness? The 10 mm. So 5/8 of 10, so we'll get 6.5 mm. Now here in the problem, which kind of weld is defined? You go for shop weld. So for the shop weld, what is the factor of safety for the shop weld? The factor of safety is taken 1.25. And where we can get this value? From table 5. Okay. So we have this sort of parameters. We have throat thickness, we have partial factor of safety, we have the effective length. So now we can calculate the strength of the weld. So what will be the strength of the weld? The effective area, LW, and the throat thickness into Fy divided by gamma MW. And this is direct tension, subjected to direct tension. Okay. So this comes out as 187.5 kilonewton. That means the strength of this weld joint is 150 kilonewton. That means this connection will safely transfer 187.5 kilonewton load. But how much load is applied? How much load is applied? It's 250 kilonewton. So it's less than the value of factor load which is applied in that joint. That means this joint is unsafe, or we cannot go with that incomplete penetrated butt weld. Now for the case of complete penetrated butt weld, what happened? The throat thickness will change. So for the complete penetrated butt weld, what our code says, the throat thickness should be equals to thickness of the thinner plate. So what is the thickness of the thinner plate? It's 10 mm. So now calculate the strength. The strength, obviously throat thickness will increase. That means effective area will increase. That means the strength carrying capacity will increase. So here we can say that 300 kilonewton. The design strength of this complete penetrated butt weld is 300 kilonewton. Obviously, it is greater than the load which is applied, or which need to transfer to the joint. So this kind of joint is safe, right? So if someone says they design that kind of joint, so obviously first check with the incomplete penetrated weld, then go for the completely penetrated weld, and then provide suitable throat thickness and length of the weld which will be required to counteract the load which is coming, or which should be, or which need to be transferred through this joint. Okay. Now this is for tension part. Now what if shear force is acting? So here I have added this example where same two plates are provided, but here what says the shear force is applied. Okay. Now find out the effective length of the weld required. Effective length of the weld required. Okay. So and what is provided here? Is anything provided? Okay, no. So the factored shear force is provided. Factored your that yield strength is provided. Now effective throat thickness, consider here in the question that which kind of weld is this? This is a single V groove weld. So what should be the throat thickness? 5/8 of the T minimum. So two plates are there, one is 12 mm and one is 8 mm. So that comes as 5 mm. And for the shop weld, or I think shop weld. So for the shop weld, we have the factor of safety 1.5 actually. So here you should write this is a field weld case. Shop weld. Oh, sorry. So for the shop weld, yes, we have 1.25. So here we can find out that the design strength will be the effective area and throat thickness divided by partial factor of safety. Now equate these two things. So we have this force. How much force we need to transfer to this joint? How much force we need to transfer to this joint? It's 300 kilonewton. So we need to equate it. 300 into 10 cube, make it in Newton, equals to, we have, don't know the LW thing, into, we have the throat thickness is 5 mm, and Fy is 250 mm, divided by root 3 into 1.25. Now from this equation you can calculate the LW. So LW means the effective length. So this effective length of 520 mm is coming. So to resist the factored shear force of 300 kilonewton, or to transfer this 300 kilonewton of shear force through this single V groove weld, we need effective length of 520 mm. Now, in previous question, if someone asked design that joint to transfer 300 kilonewton of load, so what we will need to do? You just need to calculate how much of effective length is required. Now find out, is this length, uh, can we provide this length to that joint? If yes, then go for this joint. If no, then come back again and start the design using double V groove weld. Obviously the strength will increase, that means the requirement of effective will increase, so we can provide it. If not, then we will go for another kind of weld that we call slot weld. So we'll come into it later about the slot welds. Okay, so this is how we can calculate the strength of a fillet and strength of a butt weld. So the design strength of fillet weld actually governed by the ultimate load carrying capacity of the plate, or the ultimate tensile strength of the plate and the weld material. And for the groove weld, this failure criteria or mode of failure depend on the yielding. Now let's quickly talk about the stresses. What stresses will develop within that weld. So if we have, say for example, if we have a weld area, okay, so the length, say for example, the length is LW and the effective throat thickness is TT, okay, or TE, whatever it is, and the load, direct load, maybe it may be either compressive, it may be tensile, it may be shear, individual forces will apply. So what will be the stress? So the normal stress Fa, or the shear stress, will be the load upon area stress formula. So load, this is the factored applied load P. It can be the shear force, it can be the normal force, it can be the normal force from the bending moment also. So by this way, for the individual cases, we can find out the how much stresses will develop within that kind of welded joint. So if someone says you need to transfer a load of 300 kilonewton, and you have a length of weld is say 100 mm and throat thickness is 10 mm. Now you can easily find out how much stress will develop within that joint. So this is for individual forces. When the individual forces will acting, or individual stresses, we need to calculate the individual stresses, or we are interested in calculating the individual stresses. So this thing is given on code clause 10.5.9. now what if two or three kind of loads are applying simultaneously, or in a single welded joint, then what will happen? So for that also our code says 10.5.10. This is the screenshot of this clause. This clause says, if my weld is subjected to some normal stress, this normal stress can come from axial load, or this normal stress can come from the bending moment. So due to bending, one normal stress will develop, and if this joint is simultaneously or at a time subjected to a shear force, then what should be my equivalent stress? So code says that equivalent stress should be taken as under root of Fa square. What is that Fa? This is the normal stress due to axial force. Normal stress, like if direct axial force is applied, then normal stress will be P upon T into Lw. Or if it's coming from the bending, then we have to calculate M by I is equals to F by Y is equals to E by R, that formula, pure bending formula. From that we can calculate the normal stresses. And this shear stresses, this is the direct shear stress. Either it can generate from direct shear force, or this can generate from the twisting moment. So from the twisting moment, one shear force will generate, or one shear stress will generate. So if this kind of scenarios occur during or within a welded joint, then the equivalent stress we have to calculate using that formula. And this equivalent shear stress should be less than equals to this value, Fu by root 3 gamma mb. And this Fu is the ultimate tensile strength of the parent material, or we can precisely say it is the minimum of the ultimate tensile strength of the parallel material or the deposit material, whatever we are used for that welding purpose. Okay, so here we can see an example. Here this pipe is welded with this gusset, like here this welding portion is done, and one uh, point load and one twisting moment is applied. So this, due to this force, one direct shear stress Q will develop, yes or no? This, say, let name it Q1. Due to this twisting moment, another shear stress or shear force will develop, and due to this load, what will happen? This pipe section will bend, and due to bending, one normal stress will generate. So when we will deal with this kind of welded joints, we need to consider the equivalent stress which is produced from the normal stresses and the shear stresses. So we will solve some problem regarding these stresses. Now what if normal, shear and bearing, three stresses will come together? So what happened? So here the clause 10.5.10.2, here is the screenshot of this clause. This says that if some welded joint or fillet weld is subjected to bending, bearing and shear at a time, then what will be the equivalent stress? So that equivalent stress should be equals to under root of FB square. What is FB? Shear stress due to bending, or stress, sorry, not stress, it's the normal stress due to bending. F bear, this is the stress due to bearing. So bearing stress is the load upon the contact area. Now the shear stress. Okay, so when a welded joint will subjected to different kind of loads or movements, then for the calculation of equivalent stresses, we need to use these equivalent formulas from our code. Like, let's quickly solve one example, like what I said, this pipe example. Okay, so here a pipe of 100 mm diameter and 8 mm thick. So this pipe is, the dia of this pipe is 100 mm and this is 8 mm thick, connected to 16 mm thick plate with fillet weld. So this is the 16 mm thick plate with fillet weld. Fillet weld is done on the circumference. When we see from this side, we can see that the circumference is welded like this. I will show you the picture. Now, what they said, it is subjected to a vertical load 10 kilonewton at a distance 0.5 from the weld end, and also subjected to a twisting moment. This is the twisting moment of 3 kilonewton meter. Now find out the size of the weld. What size of the fillet weld should we provide to make this joint happen, or to make this joint safe? So what should we need to do? First, we need to find out the shear stresses due to this P load. Then we need to find out the shear stress due to this twisting moment. Then we need to find out the normal stress due to the bending due to this point load. So we need to find out these three stresses. Now from these two stresses, we will get a resultant stress Q, and we will have a resultant shear stress Q, and we will have a direct or normal stress Fa. Now we have two stresses like shear and normal. So we have to go for that clause that says that the equivalent stress will be under root of Fa plus 3q square, and that should be less than equals to Fu by root 3 gamma mw. And using that equation, we can solve this problem. So let's quickly solve this problem. Which data is given? P is given, twisting moment is given, Fu, the ultimate tensile strength of plate, is given. It's a soft weld. So partial factor of safety, you can find it out from table 7. Now, what should be the design strength? Design strength of the fillet weld. Design strength per mm square. So what will be that? The Fu by root 3 gamma mw. Now here we are dealing with the fillet weld. So fillet weld, the design strength of the fillet weld will govern by the ultimate tensile strength. So here we can see 189.37 Newton per mm square per cross sectional area of weld is the design shear stress. We have calculated it. So this value we will need it later when we will equate it with the resultant stresses. So now we have to find out the stresses. So which stresses? First, due to P, we need to find out the direct shear stresses. So what will be that? So direct shear stresses, here the shear stresses due to direct load, what will be that? P upon the area. So what should be the effective area of this weld? So if we see this cross section, or if we cut this cross section over here, so what we can see? We can see this kind of welding is done on the periphery. So what will be the area? What will be the area? What is the perimeter? Twice pi r. And what is the thickness? This thickness, this is the throat thickness. So Te. So P upon area. That will be the shear stress due to direct load. Now we need to find out the shear stress due to the twisting moment. So due to the twisting moment, if we need to find out the shear stress, what do we need? The polar moment of inertia. Because remember this equation, what this says? T by Ip. T twisting moment by Ip is equals to, then we will uh, find out the shear stresses. And for the bending, this is the area moment of inertia, not the polar moment of inertia. So how we can find out the polar moment of inertia? So there can be two ways. Either we can find out Ixx and Iyy, then from that we can find out the polar moment of inertia, or we can directly use this formula. What is it? Ip is equals to r square into dA. Now what is dA portion? dA is twice pi r into throat thickness. So from here we can have the polar moment of inertia easily. That will be twice pi r cube into T. So here the polar moment of inertia we have calculated, but we don't know the size, right? So we don't know the thickness. The size we need to calculate. So consider that my effective throat thickness will be T. We will calculate the T. Then we will equate that, effective throat thickness equals to size into your K. So we can find out the size of the weld. So first thing, we have calculated the shear stresses due to direct load P. Now what we need to calculate? The shear stresses due to this twisting moment 3 kilonewton meter. So how can we calculate it? We can easily calculate it. We know the formula, Q by R is equals to T by IP. So we need this kind of this part only. If one twisting moment is applied, then throughout the cross section one shear stress will develop and which will act perpendicular to that point. So here we know that twisting moment, that is 3 kilonewton meter. So we I make it in a unit Newton millimeter. So 10 to the power 6 into 5. What is that 5? This is the R, because the total diameter was 100 mm. So what will be this R? 50 mm. Then IP. IP already we have calculated. So we have Q1 and Q2. So Q1 is directly applied like upward downward direction Q1, and Q2 will act perpendicular to that point. So what will be the resultant forces? Just under root of Q1 square plus Q2 square. That will be the equivalent shear stress. Yes or no? So this thing is written on the next slide here. So resultant shear stress. So we have the resultant shear stress like this. So for this joint, we have a resultant shear stress Q is equals to some value. Now what we need to find out? For this point load, the bending will occur, and due to bending, what will what phenomena will occur? One normal stress will occur. Like, due to that twisting moment, one shear stress will develop. Likewise, due to that bending, one normal stress will develop. What will be the value of this normal stress? So we will use the pure bending theory, and what that says, M by Ix is equals to F by Y, and this F is nothing but your normal stress. So here we can calculate the Fm, M by Ix into R. So M, what is that M? That is the bending moment due to the point load. So what is that value? The value of point load is 10 kilonewton, and it is applied which distance? Up to which distance it is applied? It is applied 0.5 from the weld face. So what will be the moment value? P into E, 5 kilonewton. Bending moment. Now for this bending moment, what kind of normal stresses will develop? That this. Now we have two stresses. One is Q, shear stress. One is normal stress. Now what do we need to do? We need to find out the equivalent stresses. How we can find out the equivalent stresses? So just go to that clause 10.5.10.1 that says your equivalent stress will be under root of fa square plus 3q square. Put all these values, so you will have the effective, or we can have the resultant or equivalent stress is this. Now what that clause 10.5.10.1 says, that these values should be less than equals to what that says, fu by root 3 gamma NW. Just equate this to what you will find. You will find the value of TE. So on the next slide, I have added it. So here, F is less than equals to Fu by root 3 gamma MB. From this clause, we are getting this information. Now, if we solve this, that comes as the T should be greater than this. And we know T is equals to, it's a 90-degree fusion phase, one plate and one pipe is there. So 90-degree fusion angle will be there. So 0.7 is, and by this way, we can calculate the size of the weld. So 5.42, we will provide 6 mm weld throughout this section to resist the stresses developed due to that point load and due to the twisting moment. So by this way, using the stress formula or using the equivalent stress formula, we can design or we can find out the stress carrying capacity. We can design that joint, like what should be the size, what should be the throat thickness, all these things. Okay. Now, let's quickly solve this problem. You guys solve this problem. Tell me what this problem says. A plate of 150 mm width and 12 mm thick. So 150 mm width, this plate 150 mm width, and the thickness, we the thickness T is 12 mm. Okay, is welded to another plate by fillet weld. So in figure here, the welding is done like this. Now what they says, find out the average shear stress produced in the weld for the full strength of the plate. For the full strength of the plate. Now tell me, what should be the full strength of the plate? If we can calculate the full strength of the plate, then we can easily, here the LW is given, we can easily calculate what should be the load carrying capacity or stress carrying capacity of this joint. So tell me, what should be the full strength of this plate? Is the full strength will governed by yielding, or is the full strength is governed by rupture? So this hole, look at the drawing, this hole is made behind the weld face. So obviously when we apply the load, this one section, the shear tear out will happen. So we have to consider the TDN value, like the design strength due to rupture of critical section, as the full strength of this plate. So what will be that? Our clause 6.3.1 says that TDN value, already we have discussed all these things. So TDN value will be 0.9 N will be the net area. So net area will be, so first we have this plate of 150 mm, and there is a hole of diameter 60 mm. So just you need to subtract that hole diameter from the width. So that 150 minus 60 into that 12 is the thickness. So this portion we got the net effective area. Fu is 410. So this much of load we need to transfer to this joint. Now what says, find out the average shear stress produced in this weld. So now we know how much load we need to transfer. How much? A pull of 318.861 into 10 to the power 3 Newton. Now how can we calculate the average shear stress? So just equate with your stress formula. So what stress formula says? Fs is equals to load upon area, and area will be Lw into Tt. Now using that equation, you can find out the value of stress. So this amount of stress can safely carried by or produced in this weld. If we need to transfer a pull equals to the full strength of the weld. Now think if the hole is made here, not here. Here is the solid plate. Now the bolt is here, and same problem is given. So what will differ? Tell me. Which thing will differ for this problem? Tell me. So for this case, what will be the area? Which area? Like if we have the hole here, now think you are applying the load, you are pulling apart this thing. So what will be the failure criteria? It will not get ruptured through 2 because the welding is already done in this portion. So what will be the failure criteria? Yielding, because only this part of the plate is vulnerable to that stresses or full strength, or to calculate the full strength of the plate. So when this hole is made within that weld area, then this kind of failure will govern by yielding. So the strength of the plate due to yielding we have to consider. So which pull or how much pull that joint is subjected to, that is the full strength of the plate due to yielding. Clear? Just think about the failure criteria. If, say for example, if this hole is made not here, if the hole is made here, what should be the full strength of the plate? And which criteria should govern the this failure of the plate? Is the rupture or the yielding? Tell me. If the hole is made here, outside the weld zone, what should be the failure criteria, or what should be the you know full strength of the plate? Obviously rupture. When you will apply the pull, this portion will fail up. But when we put the hole here within that weld zone, so when the stresses will go to that zone, the most of the stresses will get transferred. So then this solid portion will fail in, or yielding should be considered as the failure criteria for this kind of joints. Okay, clear? Yes or no? Tell me. So make sure when the problem statement is given, so look, which strength should we consider, or which strength should we consider for the full strength of the plate? So two things. If solid plate is there, we consider yielding. If we made some hole, then we reduce the area. What will happen? The rupture will be the governing strength for the failure. Okay. So here I have added this example. So nothing complicated. Just you need to calculate the full strength of the plate as a full strength of the solid plate, and that will govern by the yielding. Now come to slot and plug weld. So now it is clear how we can uh, calculate the strength of a fillet weld, butt weld, how to design them. Now come to another kind of weld. So this is a one kind of fillet weld. Why we need that kind of slot weld? When, say for example, we need to connect this plate, with this gusset, where this overlap length L1 is limited, and this L2, the depth of this plate, is also limited. So now think we need to transfer a load P, and to transfer this load P, we need, say for example, LW effective length should be maintained or should be provided. Now if so, tell me how much available length is here, or how much length is available for this connection? It's 2L1 plus L2. Now if this available length L available is less than your effective length, so how we can accommodate this extra length? So what we do, we make some slots like this, and we make the welding on the periphery of this weld. So eventually what happened? Eventually the length of the weld will increase. Okay, so if the welding is done on the periphery of the slots, we call them slot weld. And if the slots, the size of the slots are relatively small, here we can see this slot size is relatively small, and if we put all the deposit, fill the slot by using that deposit material, then we call them plug weld. So slot and plug, these are kind of fillet weld. That means while designing the stress or while designing the strength of this kind of weld, we need to keep in mind that fillet weld will govern by the ultimate tensile strength of the either the plate or the parent material or the deposit material, whatever we are depositing as a weld. So for this kind of thing, we have certain, you know, specifications, like what should be the width of this weld, or the first question, what should be the diameter of this weld. Is there any kind of limitations? Yes, there are some limitations regarding the minimum slot size, like the width of the slot. What should be the minimum width of the slot? The minimum width of the slot code says it should be maximum of 3T or 25 mm. What is that? T means T is the thickness of the thinner plate. Or for the plug weld, what should be the diameter? It also maximum of 3T or 25 mm. Now the next question, what should be the edge distance? That means, how far we can provide or how close we can provide these slots. So for this also, our code says that the distance between two adjacent slots, that should be equals to the minimum of this distance should be equals to maximum of 3T or 25. So while designing this kind of welded joint, we need to keep in mind that what should be the minimum width of these slots, what should be the minimum distance, so that we can provide the number of slots which is required to cater the extra length. Okay, so let's quickly solve one example, then this thing will get clear. So what I said, that slot and plug weld are one kind of fillet weld. So what should be the design strength? The design strength obviously is governed by the ultimate tensile strength. So for the slot weld, it's same as fillet weld. Fu, it's the ultimate minimum of ultimate tensile strength of plate or the weld material. Then this is the effective area. And for the plug weld, it's same Fu. And what is the effective area? If we provide circular slots, then pi by 4 into d square. If we provide rectangular slots, then what will happen? B into d. So it's nothing but the stress. What stress? The ultimate tensile strength, stress, and the effective area. So while designing this kind of slot and plug weld, we need to keep in mind two things. One, it's a kind of fillet weld, and their strength are governed by the ultimate tensile strength. Okay, so let's quickly solve one example, then this thing will get clear. So here we need to what says an ISMC, Indian Standard Medium Weight Channel Section, 300 mm is used to transfer a factored load. Okay, factor load is given 800 kilonewton. Now the channel section is connected to 12 mm thick gusset plate. Okay, and the design a fillet weld connection if the overlap is limited. Okay, the overlap is limited to 300 mm, and one more thing is said, the welding can only be done on the three faces, only the three faces. Okay, so here some restriction, like here the overlap length we cannot go beyond 300 mm, right? We only can weld these three faces, this face, this face, and this face. So here what we have as a constant? The length requirement, right? So what will we do? So first we will check, is this length is enough to transfer this 800 kilonewton of load? If yes, then we don't need to provide the slot. If no, then we need to make a slot and provide the slot welding. So here we have two kind of welds, like weld 1 and here weld 3. If we see weld 1 and weld 3, or we can say that weld 1 and weld 3 is same. So weld 1 we denote one kind of weld, and here weld 2. Now why I am differentiate these two things? Because this portion, that means weld 1 and below that weld 1, these two welding is done that with the flange and the bracket plate, and weld 2 portion is done between the web portion and the gusset plate portion. So obviously when we learn that how to find out the size of the weld, the maximum and minimum, specifically the minimum size of the weld will depend upon the thickness of thinner plate. Like here we have two thicknesses, 7.6 and 12 mm, and here we have two another thicknesses like 13 mm and the 12 mm gusset plate. So we need to calculate the size of the weld which is required. Then we need to check how much effective length is needed to counteract this 800 kilonewton of load. So first, quickly, go to that what should be the size of the weld. So the specification of ISMC 300 we can easily find out from the SP6. So here it is given the thickness of the flange is 13.6 mm, the thickness of the weld is 7.6 mm, all these things. So first we need to calculate the size of the weld, so first time thing, we need to find out the size of this weld one. So weld one is the connection between 12 mm gusset and 13.6 mm flange, right? This 12 mm gusset and 13.3 mm flange. So this weld and this weld is same. So what is the minimum thickness of this plate here? Is 12 mm. What should be the maximum? 13 mm. So what will be, based on the maximum size of the plate, what should be the maximum size of the, or minimum size of the weld? What should be the minimum size of the weld? If we have plates from 10 mm to 20 mm, what should be the minimum size of the weld? Our that table says it's 5 mm. And what should be the maximum size of the weld? Here we have two plates, like here we have two plates, one plate and another plate, and we have to make weld here. So for the plates, the maximum size of the fillet weld should be the thickness of thinner plate minus 1.5, thickness of thinner plate minus 1.5, so that is 10.5. So for this kind of, for this and for this zone, the size vary from 5 to 10 mm. So what size should we consider? So let's check for this portion, weld to portion, how much minimum and maximum size of weld we can provide. Then we will suitably choose one size of the fillet weld. So for this connection, tell me, this is done between 7.6 mm and 12 mm. 7.6 mm and 12 mm. So first we need to find out the minimum thickness, then maximum thickness. So what should be that minimum thickness? 5 mm. Now what should be the maximum thickness? Thickness of thinner plate minus 1.5, 6.1 mm. So which size should we consider? First, we will try to provide uniform thickness. Try to provide uniform thickness and uniform size more precisely. So let's provide 6 mm size of fillet weld. Now this 6 mm is suited for this two portion, because 6 mm is well within that 6.1 and 5 mm. And for the one part also, that vary from 5 to 10 mm. So we can take 6 mm. Now it's an iterative process. You can say, sir, we can take 5 mm also, or 5.5 mm also. Yes, you can take it. Every design process is an iterative process. So first let's try with that 6 mm. So for this 6 mm, what should be the throat thickness? The throat thickness would be K into size of the weld. So K into 6, that will be not 4, this is 6, 0.7 into 6, so 4.2 mm. So now we have the throat thickness. Now what do we need to find out? We have the force factored load which we need to transfer. We have the throat thickness. Now we can easily calculate the what or how much effective length required to transfer this load safely. So quickly solve this portion. So here this will be 6, not 4. Okay, why can't we go for 10.5 mm thickness for weld 1? What I said, first we will try to provide uniform size throughout the three sides. Yes, you can consider different thickness for here and different thickness for here also, but first as a designer, try to provide a uniform thickness, so that when this thing will install on the site, thickness or that the requirement or the uniformity should maintain. Now if we consider the 10.1 or the maximum size, this will not fit for this weld 2 portion. Is it fit for this weld 2 portion? No, because for the weld 2 portion the minimum should be 5 mm and maximum should be 6.1 mm. So let's first try it 6 mm. Or you can, you can do for this portion, you can consider 6 mm, and for the 2 portion you can consider 10.1 mm. So you just need to add them at the end of the calculations. Okay, clear? So that's why I consider 6 mm, so that I can provide uniform thickness for this entire wheel. So here the strength of weld per mm, what will happen? Fu into throat thickness, because now we will equate with the length divided by the factor of safety. So here comes 663 Newton per mm square. Now what will be the required length? Required length will be, this is per meter or mm length. So how much length will require? So total applied load divided by per meter that weld can resist or transfer load. So that comes as 1207 mm. Now, this much of effective length we have to provide to resist that 800 kilometer load safely. Now tell me, here how much length, the available length is, or how much length we can provide here? How much? 300 plus 300 plus 300. Two constraints are there. One, you can only overlap 300 mm, and you can only do welding on three faces. So my required length is that. My available length is 900 mm. So obviously, to accommodate the to accommodate this effective length which is required, we need to make some slots. So first, try to understand how much extra length should we provide. How much extra length should we provide? The required length minus available length. So 307 mm. We need to provide, or we need to have, or we have to have that 307 or more length within the joint. So how can we achieve this? So basically we have to go for slot welding. And how we can provide the slot welding? We can make slots. Now we have to understand how many slots would be there, what should be the width of this slot, what should be the length of these slots, all these things. So till now we have the understanding that we need to provide an extra length of 307 mm. Now let's provide the slots. How we can provide the slots? So for the slots we have specification that what should be the width. The width, minimum width of the slot should be maximum of 3t or 25 mm. T is the thickness of thinner plate. So here the thickness of thinner plate, what is the thickness of thinner plate here? The 7.6 mm. So 25 mm. Let's provide 25 mm of slots. Now how many slots would be there? How we can calculate this? So we can calculate easily. Like here, let's provide two slots symmetrical to the CG of the bolt. Now this amount of available length will be accommodated by that 900 whatever we have available length, plus how many length of slots we are provide, we will have if we provide two slots. So we have this length, we have this length, we have this length, and we have this length. So according to this periphery and this periphery we can weld, and this periphery and this periphery we can provide extra weld. So we don't know what should be the length of this slot. So let consider the length of the weld is x. So here how many lengths we will get? 1, 2, 3, and 4. So 4. So easily we can calculate the value of x. That x is coming as 76 mm. So let's provide, two slots of 80 mm. What is that 80 mm? This is the length of the weld, and 20 mm, this is the width of this slot. So now our connection, that connection whatever we made with the channel section to the gusset one, that can carry that 800 kilonewton load safely. Now get that point, how we can design this kind of slots well. Yes or no? Now for example, if we have slot and plug weld, or plug and fillet weld at the same time, so how we can calculate the stresses? So here one example is added. What this example says, we have what says, determine the service load carrying capacity of the connection shown in figure. And what figure says, here is a gusset and plate. Here two welding is done. One is fillet weld on these two faces. The length of the fillet weld in each faces is 100 mm, and one plug weld is also there. We can see one plug is also there, 20 mm, whose diameter is 20 mm. Now the question says determine the service load carrying capacity. So what will you do for this problem? How can we calculate the service load carrying capacity? So first you need to calculate the design load carrying capacity. Design load carrying capacity due to this fillet weld on this two portion, and the design load carrying capacity due to this plug weld. Then sum them up. That will be your design load carrying capacity. What will be the service load carrying capacity? Divided by the factor of safety, 1.5. You will get the value of service load carrying capacity. So let's quickly solve this problem. What data is given? Size of the plate is given 100 mm into 10 mm. 100 mm is width and 10 mm is the thickness. Now gross cross sectional area, obviously 100 into 10, you can calculate it. Now fillet weld size of the fillet weld, it is provided 8 mm thick fillet weld. So the size of the fillet weld is 8 mm. Now diameter of the plug weld is also given. So diameter of the plug weld is 20 mm. Which kind of weld is that? Field weld. So for this field weld, we have factor of safety 1.5. केवल 5 से हम लोग मिल जाएगा. And we have two more, stresses, like this is the ultimate and this is the yield. So first, what do we need to calculate? We need to calculate the strength due to these two sides of fillet weld. So what will be the design strength due to this two kind of fillet weld? We have the formula. What that says? LW into TT into FU divided by root 3 into gamma MW. So TT we can calculate. We know the size of the weld is 8 mm. The angle between the fusion faces is 90 degree. So it will come as 0.7. This is the throat thickness. Now you know that FU value and you know that gamma MW value. And what will be that LW effective length? 100 mm here and 100 mm here. 100 mm. So on the next slide we have total effective length as 200 mm. The design strength you can calculate using this formula, that comes as 176. So this fillet weld, this side and this side of fillet weld can carry this amount of load. Now what about this plug weld? How much this plug weld can carry the load? So for this plug weld, what do we know? The design strength or the load carrying capacity of this plug weld should be Fu multiplied the area pi by 4 into d square. Here we provide the circular one, so it will be pi by 4 into 20 square. So this plug weld can carry 49.57 kilonewton of load. So total load carrying capacity will be that plus the load carrying capacity due to the plug weld. So that comes as 226.32 kilonewton. So that much of strength these two weld combinedly can carry. Now you cannot say that this is my design strength or the joint can safely carry. One more thing you have to check. And what is this? This is the strength of plate. If the strength of plate is less than this, or if the strength of plate is more than this, right? What should be the strength of this joint? The minimum of strength of plate and strength of weld. So strength of weld we can find out this. What should be the strength of the plate? The strength of the plate should be, it obviously this there is no hole, so this plug thing is within the weld zone and this is completely filled with that plug one. So only the yielding will be the failure criteria. So what will be the strength of the plate? It will govern by yielding. The value of this will come as 227. Now we can tell that TDG, the yielding strength of the plate, is greater than PW. So we can say that the strength of the weld, whatever the strength of the weld or the combined strength of this fillet and plug weld, that amount of load we can safely transfer through this joint. So that is the design load. What will be the service load carrying capacity? Just divide by factor of safety 1.5. So this. So now we can say through this joint we can safely transfer a service load of 150 kilonewton. Okay. Now let's quickly go through another example. Here what says, you have to make a connection using fillet weld, transverse fillet weld, and some slot welds. You need to provide some slots also, or plug. More precisely, you need to provide some plug weld. So now read out the example. What says, you have two plates of 180 mm width and 10 mm thick to be connected using lap joint, and this joint is supposed to made using this transverse fillet welds and some combination of plug weld. Now we need to calculate the size of the plug weld, how many plug weld should we provide, all these things. So first, what do we need to calculate? What do we need to calculate? How much load we need to transfer. So how much load we need to transfer? The full strength of the plate. So what will be the full strength of the plate? The full strength of the plate will be governed by the yielding. So here the full strength of the plate will be 409.09 into 10 to the power 3 Newton, or we can say 409 kilonewton. Now, what should be the size of the weld? So is there any size of the weld given? Yes, 6 mm side weld is given. So we know the size of the weld. We can calculate the throat thickness. It's 0.7 into S. Now we can calculate the design strength per cross-sectional area. What will be the design stress per cross-sectional area? Fu by gamma mb into root 3. So that comes as 157.8 Newton per mm square per cross-sectional area of the weld. Now, what will be the available length? We can weld on the bottom side and we can weld this side. So available length will be 180 this side and 180 below that side. So how much of available length is here? It's 360 mm. Now we have to find out, using that 360 mm of available length, how much stress or how much force we can transfer. Rest, if this amount of length and this amount of throat thickness is enough to transfer the full strength like 409 kilonewton load, then we don't need to provide the slots. If not, then we need to provide the slot and we need to calculate the value of slot, whatever the additional stress that should be taken care by the slots. So first we need to calculate that for this length of fillet weld, how much stress we can transfer safely. So here Fu LWT2, the simple formula we know. So here we can calculate that 238.593 kilonewton load we can transfer through this joint. But actually, how much load we need to transfer? 409 point something, 409.09. So the slots we are supposed to provide, they are supposed to carry these extra loads, whatever is additional or to that fillet weld. So here 170.5 kilonewton load should be taken care by the slots. So what should be the area of slots? What should be the area of slot? That, or the plug weld. Plug, we will not make a slot here, so we will provide some plug weld here. So what should be that required area of the plug? We know that we need to transfer this amount of additional loads through these joints, and we already have the design strength per mm square of the, or per cross sectional area of the weld. So if we need to transfer, say for example 100 kilonewton load and one cross section can carry 10, so how many slots we need, or how much area should we provide? Just divide it. So here this amount of load need to carried by these plugs, and this is the strength of this weld per cross sectional area. Now we calculate the cross sectional area too. So this should be the area of these plugs. So now tell me, we can provide two plugs, three plugs, four plugs, so that this amount of area should be covered. So let's try with two plug weld. So if we provide two plug weld, so each of or area of each plug weld will be just divided. This is the length, or this is the area requirement, and we are providing, so we'll have 544. Now let's say provide 30 into 25 mm plugs here and here. So what will be the total area? 30 into 25 into 2. You can calculate. This will be 750 into 2, so 0 0 1500 mm square, which is greater than your 1080.48. That means we can say that if we provide two slots along with this transverse fillet weld of length 180 into 2 and certain throat thickness, so that this joint will transfer the full strength of the plate. So clear how we can design this kind of slots and plug welds? Yes or no? Now this weld part is sort of completed. Now we will go to the eccentric connections. First we will cover the eccentric bolted connection, and then we will go to eccentric welded connection. Then we will solve the assignments. So till now, for the butt and plug weld, if you have any questions or queries, you can ask me. Or if you understood what I try to say, or how these things will be designed, and how these calculations will be done, yes or no? Tell me. Or if you have any doubts or queries, you can ask me. So do you have, or you have understood what I try to cover? Okay. So let's quickly go to that eccentric connection part, eccentric bolted part. So we already have, talked about the direct shear connection for the bolted joint. So what will be that, if some load is applied at some eccentricity, how we can design these connections, and how we can analyze these connections. So we already have discussed, we have two kind of eccentric bolted connection. One, when the line of action of bolt, a line of action of eccentric loading and group of bolts, line of action of eccentric loading. Say for example, if we consider this plane x and y, so line of action of eccentric loading is in plane xy. The group of bolts, here you can see the group of bolts are also along this xy plane, right? So if this kind of phenomena occurs, so this we call actually say our moment connection. So case one, we say find the line of action of eccentric loading and the line of action of group of, or line of, or we can say that CG of group of bolt are on same plane. Then this can be one kind of eccentric connection. And another one, case two, find the line of action of eccentric load is in the plane perpendicular perpendicular to the group of bolt. Like here we can see the line of action of eccentric loading is, say for example, if we draw the plane here xy, so this will be along this plane. So if I draw z also here, so yz plane will be the group of bolt plane, yes. And the action applied load, the line of action of applied load will be the xy plane. So this is case two. So we will, go one by one. First we will go the case one, when the line of group of bolt and the line of action of eccentric loading is the same plane, which kind of forces will generated in the bolt, how we can design and how we can analyze these things. Then we will go to that case two. So today we will go the first case, when the line of group of bolt is in the plane with the, group of bolts. So here we have the examples. Okay, so quickly go through it. Okay, 1 second. Okay, am I audible? Am I audible? Actually the eraser is not working, so, and I need to use these slides. So let me do one thing. I will, share it again. Okay, because this I need to explain it with that pen. So let me share it again. Yeah, is it visible? Is it visible and I'm audible, right? Yes or no? Yeah, please confirm. Yeah. So first case. Now we have like case one when the line of group of bolt and the this line of action of load is in the same plane. So this eccentric load, we can see that this load is acting on this plane, and due to this load, what will happen? This due to this eccentric load, one direct shear force, that P will transfer to the CG of group of bolt, and another moment will generate due to that eccentricity. So due to that direct load P and this moment PE, which kind of forces is generated within that bolt, we need to first understand. Now here this P is the factor load and E is the eccentricity. So first let's try to understand, due to that P load and due to that PE moment, which kind of forces is actually generated within the bolt. So here we have actually two effect on bolt. One due to that direct load. So due to that direct load, what will happen? When we will design, or when we have went through that assumption, design assumption of bearing type of bolt, what we have seen, that if a group of bolt is subjected to a direct load, then each bolt will share the load equally. So if in this joint, if there are n number of bolts, if there are n number of bolt, and if the direct load is P applied, so how much reaction force will develop? So say for example we have a reaction force F1. So I am considering the reactions. If you are considering the actions, the direction of the forces will be opposite. Just that. So that F1 is generated due to direct load. So what will be the value of that F1? F1, that means on single bolt. I am considering, say for example, I am talking with this bolt. Now why I am considering this bolt, I will tell you. So this one number of bolt, due to the direct load, one upward reaction will act obviously, and the value of this reaction will be P upon N. N, if there is N number of bolt. So each bolt will carry that load equally. Now one more thing will happen. This PE moment, due to that moment, what will happen? So this P moment is applying on this direction. So obviously one set of forces will generate within the bolt which will counteract that moment. So obviously this will generate F2 forces, like in each and every bolt the F2 forces will generate. And this F2, the summation of this F2 forces or the moment of this F2 forces about the CG will counterbalance the PE moment. Okay. So how we can calculate the value of this F2? So these F2 forces are directly depend on the radial distance from the CG of group of bolt, because these F2 forces are generated due to the moment, and moment, what we know, moment is the perpendicular distance from this point to where we are taking the moment. So these F2 forces are acting perpendicular to the radial distance and they are proportional to the radial distance. That means if I place a bolt here or if I place a bolt here, obviously the bolt which is placed at more distance from the CG or far distance from the CG, that will experience more F2 forces. Now how we can calculate the value of these F2 forces? So what I said, these F2 are directly proportional to the radial distance, and these are applied perpendicular to the radial distance. That means this angle should be 90°, this angle should be 90°, this angle should be 90°, and this angle should be 90°. That means that F2, the series of F2 forces will act perpendicular to the, that radial distance from the CG. So F2 is directly proportional to R. What is R? That is the radial distance from the CG. Here this is the CG of group of bolt. From that particular bolt where we are interested to find the forces. So F2 is equals to K into R. K, that is some constant. We are now finding out the K forces, or the constant K. Now think about it. These F2s are generated just because of the moment PE. So obviously, if we consider the moment of forces F2 about CG, that will be equals to the moment whichever is applied. So summation of F2 into R. That means that is the moment due to this F2 forces about the CG, and that will be equals to the moment which is coming due to the eccentricity. So from this equation, so F2 is equals to, we know here, from here F2 is equals to, we know, K into R. So we put this K into R. So here we can find out K. K is equals to P R by summation of R square. So now put this value K in this equation. What we'll have? We'll have the value of F2 forces. The F2 force, the value of F2 force will be PER upon summation of R square. What is that P? That is the factored load. E, the eccentricity. R, that is the radial distance from the CG of the bolt in which we are calculating these F2 forces. Okay, so now for these connections, what we have seen, that due to that eccentricity, one additional moment will generate in the CG of group of bolt, and one direct load is applied. So due to the direct load, one F1 force will develop. The value of F1 will be, it's nothing but the direct load upon the number of bolts, and the F2 force, this is generated due to that moment, or to counterbalance this moment part. So that F2 part we also can calculate easily. Now we have two forces on this extreme bolt. Look at this. In this one number of bolt, we have two forces, F1 and F2. And if the angle between these two is theta, so what will be the resultant force? So what laws of parallelogram says? If we have two forces and the angle is theta in between them, then as per laws of parallelogram, the resultant stress will be F1 square plus F2 square plus 2F1 F2 cos theta. It's the basic thing. And theta is the angle between these two forces. Now we have understood that due to that type of eccentric connections, one force F1 and F2 will generate on the bolts. Now tell me, which bolt among these 5 bolts, which bolt will experience more resultant forces due to that eccentricity? Obviously, the bolts which are located far from the CG, because the bolt which is located far from the CG, the F2 force will increase, and eventually the resultant force will increase. So this 1, 2, 3 or 4, these 4 bolts will experience more resultant forces, rather if we have bolts here and here. Okay, that's why among these 4 bolt I have considered this one as a extreme bolt. Now tell me, to make this joint safely transfer some loads, or says how much load this joint can safely transfer, how we can calculate it? So first you need to calculate the resultant forces due to that P and PE at the extreme bolt. Now you need to calculate the strength of the bolt, VB, strength, that will be minimum of your shear capacity and bearing capacity. So that VB, strength of bolt, should be greater than or equals to that F, resultant stress. If this criteria satisfies, then this kind of joint we can say safe joints, or we can say if this criteria is considered with some certain of load, say P load, P is 100 kilonewton, that means that 100 kilonewton load can be transferred safely through this kind of connection. So let's quickly solve one example so that we can understand it. So here we have a connection where we have 1, 2, 3, 4 and 5 bolts. Okay, where the distances will also given, like pitch distance is this distance 80, the distance here is given also 60. So what we need to do, what the question says, find out the maximum factored load that can be carried by this connection safely. So what do we need to find out? Say for example, let's consider that P load will transfer safely through this connection. Now what do we need to find out? Due to that P load, when this P load will transfer to the CG, P and P will develop, and this P in P, F1 and F2, we need to find it out. What will be my value of F1? What will be the value of F2 on the extreme bolt? Then we have to calculate the F, the resultant force. Then if we have the resultant force, now we have to calculate the strength of the bolt. The strength of the bolt, we can find out the shear capacity and bearing capacity of the bolt. Now, if the strength of the bolt VB is greater than equals to F, then the joint is safe. So what we will do? VB, we will equate VB to F. Now here, in that F equation, that P is given. So we can, or P term will be there. So we can easily calculate the P value. So let's quickly solve this problem. So what will be the strength of the bolt? Here we have to use M20 bolt of grade 4.6. So what will be the shear capacity of the bolt? How much shear plane are there? Here two plates are there, 1 and 2. So how many shear planes are there? One shear plane. So here I have considered the shear plane is passing through the root portion. So this part will be cancelled out. Is there any kind of reduction factor is needed? No, because neither this is a long joint, neither any kind of packing plates are there. So we don't need to worry about the correction factors. So here we can calculate the shear capacity of single bolt as 45.272 kN. Now what will be the bearing capacity? We need to find out the bearing capacity. So what will be the bearing capacity of the bolt? So here I have calculated the bearing capacity. So the bearing capacity formula, we have already worked out so many problems regarding the bearing capacity. So 2.5 kb dt fu by 1.25. What will be the value of kb? That will be minimum of E by 3 d0, P by 3 d naught minus 2.50. So what will be the E value? What is the value of E? 35. What is the value of P? 80. And what is the value of d naught? We have 20 bolts, right? So d naught will be 20 plus 2, 22. So the bearing stress, and what will be the T? Here two plates are there. One thickness is 7.6 one thickness is 10 So if two plates are there, what I said, the T will be the minimum of these two. So obviously 7.6. So by this way, we can calculate the bearing capacity of. Now we can easily calculate what should be the strength of the bolt. So the strength of the bolt will be minimum of shear capacity and bearing capacity. So obviously the shear capacity of the bolt is less than the bearing capacity of bolt. So we have 45.242 kilonewton. That means we know that these bolts have the strength of 42.242 kilonewton. Now what we need to do? We need to find out that F1 force on this extreme bolt, F2 force on that extreme bolt. Then we need to find out the resultant force. Now if that resultant force F is equals to this, then we can say that yes, that amount of load we can transfer. When we equate this equation, we can find out the P value. So how we can do that? So first calculate the F1 forces. So F1 is generated due to the direct load. So here we have how many bolts are there? 1, 2, 3, 4, 5 bolts are there. So F1 will be P upon N. So P, we have considered the P amount of factor load this joint can transfer. So here we have 0.2 P. Now we have to calculate the F2 forces, and we have already derived the formula for this F2 forces. What is that? PER by summation of R square. What is the value of P into E? We know the eccentricity as 250 right? P, E as it is P, let it be. What is the value of R? What is the value of R? This R, radial distance. What will be the value of R? It's nothing but under root of, what is the value here? This is 80 So let me draw this triangle. Well, this triangle, okay. So here this bolt is there, F1 force is applying here and F2 force is applying here. This is radial distance R, this is pitch distance 80 and this is 60. So what will be that R value? R equals to under root of 80 square plus 60 square. So that comes as 100 E 250 What will be summation of R square? So we have 4 bolts and one is, at the center of, so there the R will be 0. So we have to consider 4 bolts. So 4, here we have 4 bolts. So 4 into R. For each bolt we have R 100 So 100 square. So here we have PER by R square value here. So P, this is 250 is E, R, this is the radial distance 100 and summation of R square. Why 4? Because we have 4 bolts and one bolt is at the CG. So there the R will be 0. So we did not need to consider that bolt. So that F2 value is coming as 0.625 P. So we have F1 is equals to 0.2 P. We have F2 equals to 0.625 P. Now what should be the resultant force? What should be the resultant force? So to calculate the resultant force, we need to calculate this theta value. So what will be that theta value? What will be that theta value? Tell me, what will be that theta value? So, so if we draw it again, what we can find it out, watch it carefully. So here, the bolt is here, the F1 force is applied this, and F2 force is applying here. F2. Now, this is radial distance. So this angle between F2 and R, what is that? Perpendicular distance. This is 90 degree. Okay. And this angle also, this and F, this F1, this angle is also 90 degree. Now we need to calculate the theta. Theta between F1 and F2. This is theta. So obviously, how much this angle will be? 90 minus theta. So how much this angle will be? Theta. So we need to calculate this angle only, theta. So how we can calculate the theta? Or we need the cos theta. So what will be the cos theta value? Cos theta will be 60 by R, and R value is 100. So 60 by 100. Yeah, we can calculate it. Now in the next slide, that is given. The cos theta is 60 by 100. Now we have calculated the resultant forces under root of F1 square plus F2 square plus 2F1 F2 cos theta. So put all these values. So this will be our resultant stresses at the extreme bolt. Now we have to equate this resultant stress with the strength of the bolt. So strength of the bolt was 45.272 kilonewton. If we equate it, we get the P is equals to 59.413 kilonewton. Now if says you have to calculate the force for one side, then just leave it here 59.413. If says that the bracket plate is um, you have to calculate the load for the two sides of the bracket plate, then just multiply it with 2, because one side that bracket can carry 59.43 kilonewton load, another side of this bracket can carry again 59.413 kilonewton load, because these connections in the two sides are basically the symmetric kind of connections. We go for the symmetric one only. So by this way we can analyze, or we can find out that one shear moment connection can carry the load safely, or how much load this type of connections can carry safely. Now the thing is, if say for example, if this kind of joint is provided where the P is also given, say P is equals to 100 kilonewton. Now tell me, if the joint is safe or not, what will you do? You first calculate that F1 force due to that P, F2 force due to that PE. Now you should calculate the resultant force on the extreme bolt F. Then check this F is less than or greater than the strength of the bolt value. If the resultant force is more than the strength value, then your joint will fail. If the resultant value is less than the strength of bolt value, then your joint will sustain the load. Okay. Now by this way we can analyze this kind of joints. Now how we can design this kind of joints? If for example this factor load is given, say for example 100 kilonewton load, and E we know the E, say 100 mm. So how to design them? On the previous example, the bolts are provided here, like how many bolts or group of bolts, all the details are provided here. Now if we need to design this kind of connections, what should we do, or what should be our approach, or what should be the design steps? What should be the design steps? First, we need to consider the suitable dia and grade of bolts. If not provided, then what we need to calculate? We need to calculate the strength of the bolt whichever we have considered or provided. Say for example, assume 4.6 grade, say 24 dia bolts. So for these bolts we can calculate the shear capacity of bolt and bearing capacity of bolt. So from that, there we can calculate the strength of the bolt, right? Now strength of the bolt is calculated. How many bolts should we provide? How we can calculate it? So here direct load and moment, two phenomena are occurring. So the number of bolts in each vertical row. Say for example, if we provide one row of vertical boltings, for this case the number of bolts will different, and if we provide two line of bolting, then the number of bolt in each vertical row will differ. So basically what we do, we provide an even number of rows like 2, 4. Generally we don't go beyond 4. Okay, so 1 and 1, 2 is the most conventional type of joints. So how many bolts should be there in each vertical rows due to this P direct load and the moment P? So that we can calculate from this formula. And how this formula is coming, I can show you the derivation, or I will show you the derivation how this formula is coming actually. So n number of bolt in each vertical row will be equals to under root of 6m. M, what is that m? This is nothing but your PE. N dash, what is that n dash? That n dash is the number of effective vertical, or the number of vertical line of bolting whichever you have considered. Like if you consider that we should provide 2 line of vertical bolting, then the index value will be 2. If we consider that there will be 1 line of vertical bolting, index will be 1. If you consider that yes, I will make 4 line of vertical bolting, so index will be 4. Subsequently this value will change. What is that P value? This is the pitch distance. What is that VB value? This is the strength of bolt. So now in this step we can calculate number of bolts required in each vertical load or row to counteract that P and PE, P direct load and P moment. Now we know that the number of bolts. So what will we do? We just arrange them and make the joint. We design the joint. But now what we need to do? We need to check what joint we have designed. Is this joint is safe or not? How we can ensure the safety? We can ensure the safety by finding out the resultant forces on the extreme bolt, that the resultant forces on the extreme bolt should be less than the strength of the bolt. If that is occur, then you can say whatever I have designed, this is safe. So let's quickly go through one design procedure or design example. So here we have to connect a bracket plate to a ISMB where we need to transfer 300 kilonewton of load and with an eccentricity 170 mm, where the thickness of bracket plate and thickness of this ISMB flange is given. What do we need to do? What do we need to do? First, look for is the diameter and grade of bolt is given. Yes, the diameter of bolt is given 20 mm. So write it down. Diameter of bolt is 20 mm. What should be the diameter of bolt hole? 22 mm. Grade of bolt is given. Yes, the grade of bolt is also given 4.6. So what will be the ultimate tensile strength of bolt? 4 into 100, that is 400 MPa. What will be the ultimate tensile strength of plate? We are using Fe410 plate, so that will be 410. What is the eccentricity value? 170 mm. What is the factor load we need to transfer? 300 kN. So first what we need to do? First we need to calculate the strength of the bolt. Strength of the bolt, shear capacity and bearing capacity. So we can calculate the shear capacity. So here we have only one shear plane. Consider this, that the shear plane is passing through the root. Why I am considering it? So this thing also get cleared in the last session, that the root portion is the most critical portion because the root portion has less effective area rather than the shank portion, right? So here the strength of single bolt or the shear strength of single bolt comes as 45.26 kilonewton. Now calculate the bearing capacity. So calculating the bearing capacity, we need to calculate the minimum pitch distances and end distances because we are designing now. So let pitch should be minimum pitch and edge should be minimum edge. Then calculate the bearing capacity of bolt, and the bearing capacity of bolt come as this. So what should be the strength of single bolt? So here the strength of single bolt should be minimum of shear capacity and bearing capacity. So 45.26 kilonewton. So now we know that strength of bolt is that my single bolt can carry this amount of strength. Now let's consider we will provide 2 vertical rows of bolting. Now calculate number of bolts in each vertical rows. How we can calculate it? We have that formula. What that says, n equals to under root of 6m by n dash VBP. M, we know the m value, P into E. So P value we know 300 kilonewton, E 170. So 51 kilonewton meter is the moment, that moment due to eccentricity. Okay. Now end dash, we have considered that we will provide two line of vertical bolting. So end dash will be 2. VB, this is the strength of bolt. So 45.26 into 10 cube Newton. Now what will be the pitch? So what the pitch we have considered? The pitch we have considered as 60 mm. Okay. So the 60 value, put the value of 60 here. So we need to provide 8 number of bolts in each vertical rows. Okay. Now we have the dia of bolt 20 mm. We have the grade of bolt 4.6. We know that we need to have 8 number of bolts in each vertical rows. Now we can make the arrangement happen. So how this joint will look like? So the joint will look like this. So provide pitch distance as 60 mm, and what will be the edge and end distances? Let provide 40 and 50 mm, to make the uniformity, nothing else. So here we made the connection. Now what we need to check? We need to check for the extreme bolt, whatever, due to this 300 kilonewton of loading and due to the arrangement we have made, if this extreme bolt, the resultant forces in the extreme bolt, is it sufficient to carry the resultant stress or not. So we need to calculate the F1, we need to calculate the F2 force, then we need to calculate the F resultant stresses, and we need to show that the resultant stress is less than your VB, strength of bolt value. Then if you can show, or you can conclude this thing, then we can say your joint is safe. So let's quickly do it. So here F1 direct load, for this direct load P upon N. So we have direct load 300 mm. We have 16 number of bolts, 8 this side, 8 this side. So 18. Now calculate the F2 forces. So for the calculation of F2 forces, what we need to do? PER by summation of R square. Summation of R square, R for the entire number of bolts. So here we have 18 number of bolts. So what will we do? We will calculate for this, 6 bolts. Okay. Then sorry, 4 bolts, 1 2 3 4 bolts, then we will multiply it with 4 because we have symmetric arrangements. So for the first bolt, what will be the value of R? For this first bolt, this X, say for example this is 50 mm and this one will be half of 60, that means 30. So this is 50 square plus 30 square. Now for this second bolt, what will happen? 50 square plus, what is that distance? 60 plus 30, 90. Now for this bolt, what is the R? This X is constant, this is 50, and what will be the Y value? Add one more 60, so 150 square, and this for extreme bolt we'll have 10. So by this way we can calculate the F2 force. So F2 will come as this. Now you need to calculate the resultant forces. How we can calculate the resultant forces? To calculate the resultant forces, you need the theta value. So how you can calculate the theta value? What will be the value of theta here? This angle, consider this. So cos theta will be 50 upon R, and what will be the value of R? Under root of 50 square plus this distance, total distance 210 square. So by this way we can calculate the theta also. So on the next slide, these calculations are given here, theta, and the resultant force comes out as 40.8 kilonewton. And what was the strength of the bolt? The strength of the bolt was 45 kilonewton. That means my strength of the extreme bolt, or the strength of the bolt, is more than the resultant force applied on the extreme bolt. Clear? That means whatever the joint or the whatever the arrangements we have made, this is safe. Now think, if here this criteria is failed, you saw that your resultant force is coming as 50 kilonewton and the strength of bolt is 45 kilonewton. So what will you do? You have to redesign it, and redesign it with number of, how you can minimize the resultant forces on the extreme bolt, to minimize that radial distances. So you need to reduce the pitch distances, then you can try. Or if that is also not giving you the correct result, then go for higher grade of bolts and higher diameter of bolts, then you can find out that your joint will safe. So this is the first kind of eccentric connection, where the line of action of load and line of group of bolts are on the same plane. Second kind of connections we will cover it on the next class. So here I have added the slide how this um, equation of n is equals to under root of 6 m by n dash vbp coming. These things are written here. It's very simple. Consider a one line of bolting and just equate the forces with respect to that moment, or the forces of moment with respect to the external moment. If we calculate this, you can easily find out that for one line of bolting it comes as 6m by bp, and if we consider that n dash number of vertical line is there, then this equation will turn out to be under root of 6m by n dash bp. So this all about the eccentric bolted connection. Now we need to quickly go through the eccentric welding connection. The first case, when the line of action of load and the line of action of or the plane of weld is on the same plane. For these cases, what will occur? For these cases, simple. For these cases also, a direct shear stress is developed in the weld, and another twisting moment. Due to that, twisting moment will develop. So we need to consider these two phenomena while designing that kind of um, you know welded connection. So here F1, this direct load F1 that will generate due to the direct um, force P upon the effective area, and F2. This F2 will develop or generate due to twisting moment. Why twisting moment? Why twisting moment will occur here? Why twisting moment will come here? So now think about this joint. Now I am applying the load here, and one moment will transfer to here. And why we call this twisting moment? Because if we see the cross-sectional area of the weld, if you see, it will act perpendicular to that cross-sectional area. So a twisting effect will occur and twisting moment will occur. So how we can find out the value of twisting moment? It's easily, we have the formula. If we know the polar moment of inertia, we can find out the twisting moment. Then here we have a stress due to direct shear. We have a shear stress Q1 due to P, Q2 due to the twisting moment PE. Okay, we need to find out the resultant stresses. Resultant stresses using that formula we have already discussed. This formula, Fe is equals to under root of F square plus 3Q square. Then we need to equate it with this strength, whatever we need to provide or whatever we need to transfer through this joint. So I think in example or assignments we have this kind of connection is there, but I have added two or three examples regarding this, but today due to lack of time we cannot go through in detail. But on the next class when we discuss another kind of eccentric connections, so first we will discuss this welded connection. So let's quickly solve the previous year assignments, otherwise we will run out of time. Okay, so here I have added two or three example, like for the incline loading also. So this part you can go through. If any kind of doubt, you can mail me, or on the next class I will explain these things. Or when we will solve the assignment, I think one question is there, so we will directly solve this question. Okay, so let's quickly go through the previous year assignments. So first question, what should be the effective throat thickness of the butt weld in case of incomplete penetration? What should be? We have just went through this thing. What should be? Tell me, what should be? 7/8 of the thickness of thinner part. And while we consider the calculation of stress, it will be 5/8 of the thickness of the thinner part. Now, question 2. Yeah. In case of field weld, for incomplete is 5/8. 5/8 for the calculation of stress. But normally it is taken at 7/8. Yes, 5/8 when we should consider or calculate the stresses. Yes, it should be considered as 5/8. But here the 5/8 option is not there. So we have to go for the 7/8. Right? Now, in case of field weld, the stress of the butt weld should be reduced to I have told you, reduced to 80%. Now here which one is the correct formula for calculating equivalent stress when bending, bearing, and shear both are happening? So clause 10.5.10.2.2, that F equivalent is equals to under root of FB square, FBF square, FBR square. So what will be that? What will be the value of this last, right? FB square, FBR square, FB and FBR, and 3Q square. Now tell me this question, read out this question. Match list 1 and list 2 and select the correct answer using the codes. First, what says? Look at this. A hole is made in one of the component and welding is done around the periphery of the hole. Read out the statement. A hole is made in one of the component of weld. So one of the component of the weld hole is made and the welding is done on the periphery. So welding is done on the periphery. Which option is suitable for it? Which option? What do you think? Which option is suitable for it? Periphery. The slot one. So for A, we can match that 3 is the suitable answer. Now for B, B. For B, pressure is applied continuously. Okay, pressure is applied continuously. Look at this. Seam oil, fillet oil, slot oil, plug oil, butt oil. Okay, seam oil. In seam oil, the pressure is applied continuously. Now, joining two surfaces approximately at the right angle to each other. So write it the statement and find it out which should be yes, fillet weld. Now last structural member are subjected to direct tension or compression. We have seen that is the butt weld. So now match it with your answer. Which one is the correct option? I think the D will be correct answer. Yeah. Okay. Now go to the next question. Yeah. So this question says a pipe is connected to a plate with fillet weld done along its perimeter. The weld is subjected to combined loading and it is found that resultant shear stress of magnitude, the value of resultant shear stress is given and bending stress is also given. Now find out the minimum size of the fillet weld. Find out the minimum size of the fillet weld. So what do we need to do? Here one shear stress is applied and one normal stress is applied. So what do we need to calculate? We need to calculate the resultant stresses. And how we can calculate the resultant stresses? Using that formula. Fe is equals to under root of Fa square plus 3Q square. So calculate the resultant stresses. It will comes out as 757.47 by Te. Because that we ultimately we need to find out the effective throat thickness. Throat thickness is equals to K into S. If we can find out the T value, we can find out the S. And this K value is 90-degree fusion phases. So this is 0.7. So we need to find out ultimately the throat thickness. How we can find out the throat thickness? So this is the equivalent stresses or resultant stresses. So we need to equate with this equation. So if we equate with this equation, we can find out that our TE should be greater than 4 mm. And we know TE is equals to, what is the value of TE? TE value is equals to K into S. So what will be the value of S? So S will be equals to 4 by 0.7. So K into S. So this comes as 5.71. So 6 mm is the right answer. Clear? Okay. Now move to the next question. Yeah. It's a nice question. Two plates of 10 mm and 20 mm are welded by two different methods of welding. First, fillet weld and butt weld. If the weld area for both methods are same, find out the ratio of design shear strength in butt weld and fillet weld. Okay, design shear strength in butt weld governed by yielding, but the design shear strength in fillet weld governed by Fu, the rupture value. So this will be the difference. So design shear strength of the fillet weld, what will be that? Fu into effective area by root 3 into gamma mw. Fu. Okay. Now design shear strength of the butt weld, Fy. That is the basic difference. I have already discussed the mode of failure for the fillet weld is governed by the rupture and mode of failure of the butt weld. Think about it. Butt weld, you make a solid plate. So it will govern by the yielding part. So the ratio will be Fy by Fu. So what will be the value of Fy and Fu? So that will comes as 0.61. So 0.61 will be my correct answer. This is a very good question. This kind of question may come in your competitive examination too. So you need to clear that which is the mode of failure or the failure criteria for the you know butt weld, and what is the mode of failure criteria for the fillet weld. Okay, so now move to the next question. Okay, here we have similar kind of example, that calculate the load F. We have just sometimes back we have solved the calculate the value of load of P, which that joint can safely transfer. So what do we need to do here? We need to calculate the resultant stresses in bolt 1, that F1, F2. Then we need to calculate the resultant stresses. Then we equate the resultant stresses to the strength of the bolt. So let's quickly do it. So the strength of the bolt value, take the bolt value as 70 kilonewton. What is the bolt value mean? The strength of the bolt is given. The strength of the bolt is 70 kilonewton. Now, what do we need to calculate here? We need to calculate these radial distances, right? R value. What is the extreme bolt? Here 1, 4, 6 or 3. You can take any of them. So I am considering this one number of bolting. So what will be that R value for this one bolt? R value for this one bolt will be under root of that 65 square plus this square. So this comes as 95.25 mm. Clear? Now what will be the R value for this 2 and 5 bolt? That will be only this part is 140 mm. So half of this, that means 70 mm. So we have two radial distances. One is R1 95.52 and R2 70 mm. So now what do we need to calculate? We need to calculate the value of F1 and we need to calculate the value of F2. So F1 we can easily calculate. F1, say name it F1. So what will be the value of F1? That will be equals to F upon number of bolts. How many bolts are there? 6. So here F by 6. Now I need to calculate the value of F2. So F2 will be FER by summation of R square. So here this R will be this R1, right? R1. And so while calculating the summation of R square, we need to consider that for 1, for 4, for 5, for 2, all of these ports. So quickly solve it. So F1R, the resultant force, because we need to calculate first the F2 forces. F2 is I'm getting here F2, because the summation of R square is here, R1 square, R2 square, R3 square. You can calculate it. R1, that means this is the radial distance for bolt 1. R2, this is the radial distance for bolt 2. R3, this is the radial distance for bolt 3. So you can calculate this like this. So F1 we have calculated, this come as F by 6. F2 this coming as this. Now we need to calculate the angle between these two. So here we have F1, we have F2. Now if we know the angle between them theta, you can easily calculate the resultant forces. So we need to calculate this theta. So what will be the theta here? What will be the theta here? I have just explained sometimes back. What will be that theta? So directly write it down. Cos theta will be equals to this value. What is the value? This value. This value is 70 divided by what is the R? That is 95.5. Now you can calculate the cos theta value. If you can calculate the cos theta value, or then you can find out the resultant forces. So theta will eventually come out 42.88 degree. You can check it, no problem. So this is the resultant force on the extreme bolt. Now equate with bolt value. So 0.432 F is equals to, what is my bolt value? 70. So what will be the F value? 70 divided by 0.432. That will come as 141.3 kilometer. So the answer which is near to that value, that will be the correct answer. So what is that answer here? How much is coming? 141. So C will be the correct answer. Okay. Now one more question left, that is for the welding joints. So here, look, we have the first case, option C. Yes, option C will be the correct answer. Option C. Yes, option C will be the correct answer. Now for this connection, here we have the first case where the load of applied load and the you know group or the plane of weld on the same plane. So two forces will occur. One, due to that direct load, direct shear stress will develop, and due to the twisting moment here at the CG of the bolt, one twisting moment will occur, P into E. For this twisting moment, we need to calculate the shear capacity. Then we have to calculate the resultant and find out is my joint is safe or not. So try to solve it, okay, and just focus on it. It's a simple thing. So here what is given here, just look at it. What is given here? Load is given. Is the eccentricity is given? No. What is the value of eccentricity? Here from CG of bolt, here the CG from the CG of bolt here. So what do we need? We need to know this distance, this distance. Is the distance is provided? Yes, this distance is provided, X. Look, area from area from BC, so 29.3. So we can calculate the E value. What will be the eccentricity value? E will be 170, this, plus we need to go up to here. So that will be 120 minus 29.38. This is the eccentricity. Now we know the eccentricity, we can calculate the value of twisting moment. What will be the value of twisting moment? P into E. So we can calculate the P into E. Now with respect to the twisting moment, how much shear stress will develop, we need to calculate. So how much shear stress will develop? How we can calculate this? So that we can calculate that T by IP is equals to Q by R. So on the next slide, we have added this thing. So X is the distance. So what will be the eccentricity? It's 260 mm. What is the polar moment of inertia? The polar moment of inertia is given on your question. It's 5.78 into 10 to the power 60. The polar moment of inertia also given. Now what is the area of weld? So we know my CG is here. CG is here. So that will be this, right? What is that? 170. This is 170, not 70. This is 170. So why you are saying 70? It's 170. 170 plus this value, right? 170 plus this small distance. So it comes as 260.62. Okay. Now what will be the area? How much area should I have? Area here on this side, on this side, and on this side. We have three areas. So what will be the area of this oil? So area will be 2 into for this side and this side, 2 into 120 into T. And for this side, what is the width of this side? 250 mm. 250 into T. T is the thickness or throat thickness. So total effective area is that. Okay. What is the radial distance R here? What is the radial distance R here? R. What will be R? So if I draw it like this, R. So here we have this value. This value. This value means 120 minus 29.38. And what is that value? This is 250 into half, 250 by half. So 250 divided by 2, 125. So what will be the R value? Under root of 125 plus 120 minus that square, right? So we have the maximum radial distance 154.39. What should be the twisting moment? P into E, that much. What should be the shear stress developed due to the twisting moment? P by or T by IP is equals to F by R. So here the shear stress due to twisting moment, here it is denoted by FB, or you can QS, you can denote it like that. So this value is coming is this. Now what will be the value of stress due to the direct shear? It's nothing but P, the direct load, that means 60 kilonewton divided by area, total area of the weld. What is the total area of the weld? We have calculated 490 T. So here we have calculated two stresses. One is PB and one is PS. What is the theta? What is the value of cos theta here? Cos theta will be this by r. So this value is coming out as 120 minus 29.38. How much value is coming? 90 point something, 90.62 divided by r. What is the value of r? 154.39. So 154.39. That will be the value of cos theta. So we can calculate the resultant stress. Like, now, what will be the strength of weld? What will be the strength of the weld per mm square? It's nothing but Fu by root 3 gamma m naught. Now equate this resultant stress with the strength of the weld per mm square. You can calculate the throat thickness. When you know the throat thickness, what will be the S value? Throat thickness will be equals to K into S. So S will be equals to throat thickness divided by K. So it's come out for mm. So it's kind of simple thing. Like in a bolted connection, when due to the eccentricity F1 and F2 will develop, here what happened? Two kind of shear stresses will develop. One due to the direct load, one due to the twisting moment. So that's all for now. So if you have any queries, you can ask me, or if you have any doubts. Yeah, actually, you will get this link directly. You know, when you log in to the NPTEL, particularly the design of steel structure course, at the end you will see one link like the online interactive session. You click that link, you will direct it to a page, Excel sheet. There you can see that me and one of my fellow um, um, scholar, the details of these things are given, like the video link, the link to the lecture notes, all these things are given. Or else I can share it also, no problem. Tell me if you have any doubts regarding today's session. We can discuss, or else we can end the session here, and we will meet on next week. So do you have any queries or questions, or you have all the doubts have been cleared? You need to practice it. Okay. So if you have you know don't doubts, if you have any doubts, then we can conclude here. Good night. Can I ask doubt of previous week session? Yes, you can ask. Tell me. No problem.